Hello there, and welcome to Silent Scientist. Tonight, we drift into the boundless expanse of the cosmos, where time moves differently, where light takes billions of years to reach our eyes, and where every atom in your body was once forged in the heart of a distant star. The universe is not a place of chaos or fear. It is a place of gentle rhythms, patient processes, and breathtaking beauty unfolding across timescales so vast that our worries dissolve into insignificance. In this quiet journey through space, we will explore the most calming, most wonder-filled facts about the cosmos. You will discover how the universe moves with purpose, how silence fills the void between stars, how light itself becomes a time machine, and how even the most powerful forces in nature operate with a kind of cosmic grace. These are not just facts. They are invitations to see yourself as part of something infinitely larger, infinitely older, and infinitely more peaceful than the rush of daily life. If you enjoy these gentle explorations into the science that surrounds us, I invite you to like this video, subscribe to Silent Scientist, or share a thought in the comments below. It helps other peaceful minds find their way here, one dreamer at a time. But for now, let your shoulders drop, let your breath deepen, and let the universe carry you toward rest. Let us begin. The gentle nature of cosmic time. Time is not what it seems. Here on Earth, we measure our days in hours and minutes, rushing from task to task, watching the clock as if it were an adversary. But step beyond our atmosphere, venture out into the depths of space, and time itself transforms into something fluid, patient, and profoundly peaceful. According to Einstein's theory of general relativity, time moves differently depending on where you are and how fast you are traveling. Near massive objects like stars or black holes, time slows down. The stronger the gravitational pull, the more time stretches and bends like warm honey. This is not science fiction. It is a measured, confirmed reality that has been tested countless times. Astronauts aboard the International Space Station, orbiting Earth at 17,500 miles per hour, experience time slightly differently than we do on the surface. After 6 months in space, they return having aged about 5,000ths of a second, less than those who remained on Earth. The difference is tiny, imperceptible to our senses, but it is real. Time, for them, moved just a fraction slower. Now imagine traveling not around Earth, but across the universe. Scientists studying ancient quasars, those brilliant beacons powered by supermassive black holes in the early cosmos, have discovered something extraordinary. When they observed quasars that existed just 1.5 billion years after the Big Bang, they found that time in those distant regions appeared to move 5 times slower than it does today. Events that would unfold in one day for us would take 5 days in that ancient epoch. Not because the universe was different in some fundamental way, but because the expansion of space itself stretches time as light travels across billions of years to reach our telescopes. This phenomenon, called cosmological time dilation, means that when we look at distant galaxies, we are not just seeing them as they were long ago. We are watching them move through time at a different pace. A supernova explosion that takes weeks to brighten and fade in a nearby galaxy will appear to last months when it occurs in a galaxy billions of light years away. The universe itself is telling us that time is not a rigid ruler. It is flexible, patient, and intimately connected to space. What does this mean for you, lying here in the quiet of this moment? It means that the very fabric of reality is gentler than we imagine. There is no universal clock ticking the same for everyone, everywhere. Time adapts. It flows. It gives way to the presence of mass and the journey of light. In the grand scheme of the cosmos, there is no rush. Events unfold according to the curvature of space-time, according to the distance light must travel, according to the ancient rhythms set in motion more than 13 billion years ago. Consider this. If you could somehow stand near the event horizon of a black hole, that boundary beyond which not even light can escape, time for you would slow to an extraordinary degree compared to the rest of the universe. A friend watching from a safe distance would see you move in extreme slow motion, your every gesture stretched across hours, days, even years. But from your perspective, nothing would feel different. Your heartbeat would sound normal. Your thoughts would flow at their usual pace. Time would seem to pass as it always does. The strangeness only appears when comparing different regions of space-time. This is the universe's gift to us. Time is not an oppressor. It is a companion that adjusts itself to the circumstances of existence. Near massive objects, it lingers. In the emptiness of intergalactic space, it flows freely. And across the expanding cosmos, it stretches like a soft melody played on an instrument too large to see. There is a deep comfort in knowing that time, at its most fundamental level, is not fixed. When we feel rushed, when the hours seem to slip through our fingers, we can remember that time itself is only one way of measuring change. The universe does not hurry. Stars take millions of years to form. Light from distant galaxies travels for billions of years before reaching us. Supermassive black holes drift through space, patient and silent, accumulating matter grain by grain across eons. Even GPS satellites orbiting above us must account for time dilation to function properly. Their clocks tick slightly faster than clocks on Earth's surface because they are farther from our planet's gravitational pull. If engineers did not adjust for this difference, the satellites would lose synchronization within minutes and our navigation systems would fail. Every time you use a map on your phone, you are depending on Einstein's equations, on the knowledge that time flows at different rates depending on where you are. The universe is teaching us patience. It is showing us that there is no single, absolute now. Every observer has their own experience of time, shaped by motion and gravity, by distance and mass. In a very real sense, the present moment exists differently for each of us. And if time can be so flexible, so responsive to the conditions around it, perhaps we too can learn to move with that same gentle adaptability. Scientists have measured this effect not just with satellites and quasars, but with ordinary clocks placed at different altitudes. A clock on a mountaintop runs faster than a clock at sea level. The difference is measured in nanoseconds, but it accumulates. Over the course of a human lifetime, a person living at high altitude will age slightly more than someone living at sea level. Not enough to notice, but enough to prove that time is not uniform. This is the universe operating not with violence or chaos, but with elegant rules that bend and flex according to circumstances. Gravity does not break time, it shapes it. Motion does not shatter time, it stretches it. And expansion does not erase time, it gives it room to breathe. So as you lie here, know that the time you're experiencing right now is yours alone. Somewhere in a distant galaxy, time is moving differently. Near a black hole, it slows to a crawl. In the emptiness between galaxy clusters, it flows freely. And all of it, every moment, is part of the same cosmic fabric, woven together by forces we can measure, predict, and understand. Time is not your enemy. It is a river with many currents, some fast, some slow, all flowing toward the same endless ocean. And you, here in this moment, are part of that flow, gently, patiently, timelessly. Stars, the universe's night lights. Look up on a clear night, far from city lights, and you will see thousands of stars scattered across the darkness like grains of luminous sand. Each one is a sun, burning with nuclear fire, converting hydrogen into helium in its core and releasing light that travels for years, decades, centuries, or millennia before reaching your eyes. The stars you see tonight are not as they are now. They are as they were when their light began its journey. You are seeing into the past with every glance upward. There are more stars in the universe than grains of sand on all the beaches and deserts of Earth. This claim, made famous by astronomer Carl Sagan, was once thought to be poetic exaggeration. But scientists at the Australian National University conducted a study and discovered it was true. When they calculated the number of stars in the observable universe, approximately 300 sextillion, or 3 followed by 23 zeros, and compared it to the estimated number of grains of sand on Earth, the stars outnumbered the sand. The universe is more abundant, more generous with its light than we can easily comprehend. Our own sun is a perfectly ordinary star. It is not the largest, not the brightest, not the most unusual. It sits in the middle range of stellar sizes and temperatures, a yellow dwarf star that has been burning steadily for about 4.5 billion years and will continue for another 5 billion before it begins to change. In cosmic terms, The sun is middle-aged, reliable, and calm. It rises each morning, not because it moves, but because Earth rotates, carrying us toward its light. The sun does not chase us. We turn to meet it day after day in a dance that has continued since our planet formed. There are 300 billion stars in our Milky Way galaxy alone. Each one is a world unto itself, generating energy through nuclear fusion, a process so powerful that a pinhead of material from the sun's core would kill a human from over 100 miles away. Yet, from our safe distance of 93 million miles, the sun feels gentle. It warms our skin. It grows our food. It lights our days without overwhelming us. Distance transforms danger into comfort, fury into nourishment. Stars are born in nebulae, vast clouds of gas and dust drifting through space. These stellar nurseries are among the most beautiful structures in the cosmos, glowing in shades of red, blue, and violet as newborn stars ignite within them. The process takes millions of years. Gravity pulls matter together, slowly, patiently, until the core of the collapsing cloud becomes dense and hot enough for nuclear fusion to begin. At that moment, a star is born. Light pushes outward from the core, balancing gravity's inward pull, and for millions or billions of years, the star will shine. Not all stars are the same. Some are red giants, enormous and cool, hundreds of times wider than the sun, but with surface temperatures lower than our own star. Others are blue supergiants, massive and scorching, burning through their fuel so quickly that they live only a few million years before exploding in supernovae. The smallest stars, red dwarfs, are dim and cool, but they are the most common type in the galaxy and can burn for trillions of years, far longer than the current age of the universe. The nearest star to Earth, aside from the Sun, is Proxima Centauri, a small red dwarf located 4.2 light-years away. That means the light we see from it tonight left its surface more than 4 years ago. If Proxima Centauri suddenly vanished, we would not know for another 4 years. The universe operates on a delay, a cosmic speed limit set by the speed of light, and nothing can travel faster. Information, energy, influence, all of it moves at this ultimate pace, roughly 186,000 miles per second. Fast beyond human comprehension, yet slow enough that the universe becomes a time machine simply by existing. Some stars pulse. They expand and contract in regular rhythms, brightening and dimming over days, weeks, or months. These are called variable stars, and astronomers use them as cosmic yardsticks to measure distances across the universe. One type, called a Cepheid variable, brightens and dims with such regularity that its period of pulsation reveals its true brightness. By comparing that intrinsic brightness to how bright it appears from Earth, astronomers can calculate how far away it is. These stars are lighthouses in the dark, helping us map the structure of the cosmos. Other stars come in pairs, orbiting each other in graceful dances that can last for days, years, or centuries. These binary stars are more common than solitary ones like our Sun. Some pairs are so close they share an atmosphere, pulling matter from each other in streams of glowing gas. Others are so distant that each star seems alone, yet they remain bound by gravity, circling an invisible point between them, partners across the void. When massive stars die, they do not simply fade away. They explode. A supernova can briefly outshine an entire galaxy, releasing as much energy in a few weeks as the Sun will produce in its entire 10 billion year lifetime. The explosion scatters heavy elements, carbon, oxygen, iron, gold, across space, seeding the cosmos with the raw materials for planets and life. Every atom of iron in your blood, every atom of calcium in your bones was forged in the heart of a dying star billions of years ago. You are made of stardust, and so is everything around you. But not all stellar deaths are violent. When a star like the Sun exhausts its fuel, it swells into a red giant, engulfing the inner planets, then gently sheds its outer layers into space, creating a glowing shell called a planetary nebula. These nebulae are among the most beautiful objects in the sky, symmetrical and colorful, like cosmic flowers blooming in the dark. At the center of each sits a white dwarf, the exposed core of the dead star, no larger than Earth, but with a mass comparable to the Sun. A teaspoon of white dwarf material would weigh about 5 tons on Earth. Gravity compresses matter into extraordinary densities, creating objects that defy everyday intuition. The light from stars does not just travel, it interacts. It carries energy, momentum, and information. When starlight strikes a leaf on Earth, it drives photosynthesis, converting carbon dioxide and water into sugar and oxygen. The energy stored in that sugar came from a star, our Sun, which got it from nuclear fusion, which came from the gravitational collapse of a cloud of hydrogen billions of years ago. Life is powered by starlight, and starlight is powered by gravity. Everything is connected. Some of the stars you see in the night sky no longer exist. They burned out, exploded, or faded centuries or millennia ago, but their light is still traveling toward us, carrying the image of what they were. When you look at the sky, you are not seeing the universe as it is now. You are seeing a patchwork of past moments, each star frozen at a different point in history. The cosmos does not present itself in the present. It offers a gallery of memories, light preserved across time. There is a category of stars so cold they barely shine, brown dwarfs, sometimes called failed stars, are too small to sustain the fusion of hydrogen in their cores. They glow faintly from residual heat, cooling slowly over billions of years. Some brown dwarfs have surface temperatures only a few hundred degrees above absolute zero, cooler than boiling water, cooler than a candle flame. They drift through space, dim and quiet, reminders that not all celestial objects burn with fury. Some simply glow gently in the dark. Stars do not make noise. Space is a vacuum, and sound requires a medium like air or water to travel through. But if we could somehow hear them, if we could translate their electromagnetic radiation into sound waves, stars would hum, rumble, and sing. Scientists have done this. They have taken data from stars, pulsars, and other cosmic objects and converted it into audible tones. The result is eerie and beautiful. The universe has a soundtrack, though we cannot hear it with our ears. Every star is a balance. Gravity pulls inward, trying to collapse the star into nothingness. Fusion pushes outward, trying to blow it apart. For most of a star's life, these forces are perfectly balanced. The star neither grows nor shrinks. It simply shines, stable and calm, a sphere of plasma held together by invisible forces. This balance can last for billions of years, longer than continents exist, longer than mountains stand, longer than oceans churn. Stars are patient beyond measure, and when we look at them, we are reminded that we are not separate from the cosmos. The light entering your eyes right now has traveled across space, carrying energy that began in the core of a star. Your body, built from atoms formed in stellar furnaces, is detecting photons that left distant suns years, decades, or centuries ago. You are part of the system. You are made of the universe observing itself. And the stars you see are not distant and alien. They are family, ancient and enduring, lighting the way through the dark. Nebulae, cosmic clouds of color. If stars are the universe's nightlights, then nebulae are its watercolor paintings, vast clouds of gas and dust that glow in shades of red, blue, green, and violet, sculpted by gravity, starlight, and stellar winds into shapes that resemble flowers, butterflies, hourglasses, and abstract art. These are not mere clouds. They are the nurseries where stars are born, the shrouds left behind when stars die, and the galleries where the cosmos displays its most exquisite beauty. The word nebula comes from the Latin for cloud or mist, and that is exactly what they look like through a telescope, ghostly wisps of light floating in the blackness of space. For centuries, astronomers could not tell nebulae apart from distant galaxies. Both appeared as faint smudges of light. It was not until the 20th century, when larger telescopes and photographic techniques improved, that the true nature of nebulae was revealed. They are not distant islands of stars. They are nearby structures within our own galaxy, made of the same hydrogen and helium that fill the space between stars, only gathered into regions dense enough to glow or block light. There are several types of nebulae, each with its own story to tell. Emission nebulae shine because the gas within them is heated by nearby stars. Ultraviolet light from hot young stars strips electrons from hydrogen atoms, a process called ionization. When those electrons recombine with the atoms, they release energy as visible light, primarily in a red wavelength characteristic of hydrogen. These nebulae glow like neon signs, their colors determined by the elements they contain. Oxygen glows blue and green, sulfur glows red. Together, they create the vibrant hues seen in images of nebulae like the Orion Nebula or the Eagle Nebula. The Orion Nebula is one of the most famous and easily visible nebulae in the night sky. It lies about 1,500 light-years from Earth in the constellation Orion, just below the three stars that form the Hunter's Belt. On a clear winter night, even without a telescope, you can see it as a fuzzy patch of light. Through a telescope, it reveals itself as a glowing cloud with swirling structures and bright stars embedded within. At its heart is a group of 4 massive, young stars called the trapezium, which illuminate the entire nebula with intense ultraviolet radiation. These stars are only a few 100,000 years old, infants in cosmic terms, and they will continue to shape and reshape the nebula as they age. Nebulae like Orion are stellar nurseries, places where gravity is pulling gas and dust together to form new stars. Within the densest regions, called Bok globules, small pockets of material are collapsing under their own weight. These dark knots of gas may look empty in images, but they are actually the birthplaces of future stars. Over millions of years, the collapse continues until the core becomes hot enough to ignite fusion. A star is born, and its light begins to push away the remaining gas, carving cavities in the nebula. The process is slow, gentle, and inexorable. Not all nebulae are places of birth. Some are monuments to death. Planetary nebulae, despite their name, have nothing to do with planets. They earned the name in the 18th century when astronomers using small telescopes thought they resembled the pale disks of planets like Uranus or Neptune. In reality, planetary nebulae are the outer layers of dying stars, cast off into space when the star exhausts its fuel and swells into a red giant. The core of the star remains behind as a white dwarf, a dense ember slowly cooling over billions of years. But the outer layers expand outward, forming a glowing shell that can be seen from thousands of light years away. These nebulae come in astonishing variety. Some are spherical, like soap bubbles. Others are hourglass-shaped, with 2 lobes stretching in opposite directions. Some resemble butterflies, flowers, or eyes staring out from the void. The shapes are determined by magnetic fields, the rotation of the dying star, and interactions with companion stars or planets. No 2 planetary nebulae are alike, and astronomers are still studying how such intricate structures form at the end of a star's life. One of the most famous planetary nebulae is the Helix Nebula, sometimes called the Eye of God. Located about 655 light-years away in the constellation Aquarius, it is one of the closest planetary nebulae to Earth. Through a telescope, it appears as a ring of glowing gas with a faint, dark center where the white dwarf sits. The nebula is roughly 3 light-years across, meaning it would take light 3 years to travel from one side to the other. Its colors, shades of red, green, and blue, come from different elements glowing at different temperatures. It is a portrait of a star's death, beautiful and serene, a reminder that endings can be as striking as beginnings. Another type of nebula, reflection nebulae, do not glow on their own. Instead, they reflect the light of nearby stars, much like how clouds on Earth reflect sunlight. These nebulae appear blue because blue light scatters more easily off small dust particles, the same reason Earth's sky appears blue. Reflection nebulae are often found near star-forming regions where young, hot stars illuminate the dust and gas from which they formed. Then there are dark nebulae, regions so dense with dust that they block the light of stars behind them. These appear as black patches or dark lanes cutting across bright nebulae or the Milky Way. They are not empty. They are filled with material, cold and dense, waiting for gravity to pull it together into new stars. The most famous dark nebula is the Horsehead Nebula in Orion, a silhouette shaped like a horse's head and neck rising from a glowing cloud of gas. It is a favorite target for astrophotographers because of its striking contrast and recognizable shape. Some nebulae are the remnants of supernova explosions. When a massive star explodes, it does not simply vanish. It leaves behind a rapidly expanding shell of gas and debris called a supernova remnant. These remnants can be hundreds of light years across, glowing with energy from the shock wave plowing through the surrounding space. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in the year 1054, is still visible today through telescopes. At its center is a pulsar, a rapidly spinning neutron star left over from the explosion, emitting beams of radiation like a cosmic lighthouse. Nebulae remind us that the universe is not static. It is constantly recycling itself. Gas collapses into stars. Stars burn for billions of years, then die and return their material to space. That material drifts through the galaxy, eventually gathering into new nebulae, which birth new stars, which die and spread their atoms once more. The cycle has been repeating for over 13 billion years, and it will continue for trillions more. Every element in your body, every breath you take, every atom in the air around you was once part of a nebula, then a star, then a nebula again, traveling through space and time until it became part of you. Hubble Space Telescope has captured thousands of images of nebulae, revealing details invisible to ground-based telescopes. The colors in these images are often enhanced or assigned based on specific wavelengths of light, but the structures are real. The pillars, the filaments, the cavities carved by stellar winds, all of it exists. Nebulae are not smooth or uniform. They are textured, layered, and dynamic, shaped by forces we are only beginning to understand. There is a nebula called the Boomerang Nebula, located about 5,000 light-years from Earth. It is the coldest known place in the universe, with a temperature of negative 272 degrees Celsius, just 1 degree above absolute zero. This is colder than the cosmic microwave background radiation, the faint glow left over from the Big Bang, which permeates all of space at a temperature of about negative 270 degrees Celsius. The Boomerang Nebula achieves this extraordinary cold because it is expanding so rapidly that the gas within it cools as it spreads out, much like how compressed gas cools when released from a pressurized canister. It is a cloud of ice crystals and molecules drifting through space, a frozen monument to a dying star. NASA has turned some nebulae into sound through a process called sonification. By mapping brightness to volume and color to pitch, scientists can translate visual images into audio compositions. The result is hauntingly beautiful. High-pitched tones correspond to bright blue regions. Low tones represent red areas. Stars within the nebula become chiming notes. Listening to these sonifications, you can hear the structure of the nebula, its swirls and layers, its bright centers and faint edges. The universe, silent in space, becomes a symphony when translated into sound. Nebulae do not exist in isolation. They are connected to the larger structure of the galaxy, part of the interstellar medium, the thin soup of gas and dust that fills the space between stars. Most of this material is hydrogen, the simplest and most abundant element in the universe. But it also contains helium, oxygen, carbon, nitrogen, iron, and trace amounts of nearly every other element. This is the raw material from which everything is made. Planets, moons, asteroids, comets, and living organisms all trace their origins back to the interstellar medium, concentrated and transformed through the life cycles of stars. When you look at a nebula, whether through a telescope, in a photograph, or even just imagining it, you are looking at potential. It is a place where the universe is still deciding what to create next. It is matter waiting to become stars, planets, perhaps even life. And it does so without hurry, without force, simply following the patient pull of gravity and the gentle pressure of starlight. Nebulae are proof that creation does not require violence. It requires time, space, and the slow gathering of what is already there. They are beautiful not because they are rare, but because they are inevitable. Every galaxy has them. Every star-forming region is surrounded by them. They are part of the endless cycle of birth and death that keeps the universe alive. And in their colors, their shapes, their glowing presence against the dark, they remind us that even the end of something can be luminous. The silent symphony of space is often called a vacuum. And that is true. It is the absence of air, of atmosphere, of the medium that sound waves need to travel. On Earth, sound moves through air as vibrations, molecules bumping into each other in a chain reaction that carries energy from a source to your ears. But in space, there are no molecules to bump. The density of matter is so low, sometimes fewer than 1 atom per cubic centimeter, that sound cannot propagate. If you were floating in the void between stars and someone shouted your name, you would hear nothing. the universe is silent. Or is it? The absence of sound does not mean the absence of vibration. Space is filled with electromagnetic radiation, from radio waves to gamma rays, moving at the speed of light, carrying energy across vast distances. These waves do not need a medium. They travel through the vacuum itself, ripples in electric and magnetic fields. And although we cannot hear them directly, we can detect them, measure them, and translate them into forms we can perceive. Scientists at NASA have done exactly that. They have taken data from stars, black holes, nebulae, and other cosmic objects, and converted it into sound through a process called sonification. The result is a library of eerie, beautiful audio recordings that let us hear what space would sound like if sound could travel there. A supernova remnant sounds like a deep rumble. A pulsar sounds like a rhythmic ticking. A quasar sounds like a rising and falling hum. These are not the actual sounds of these objects. They are interpretations, translations of invisible light and radiation into audible tones. But they give us a way to experience the cosmos through a different sense, to feel its rhythms and pulses as if it were speaking to us. The cosmic microwave background, the faint glow of radiation left over from the Big Bang, has also been turned into sound. It is a low hiss, almost like static, but within it are tiny fluctuations, variations in temperature and density that correspond to the seeds of galaxies and galaxy clusters. When these fluctuations are amplified and translated into audio, they become a kind of cosmic music, the first sound of the universe echoing across 13 billion years. Even black holes, those regions of space-time where gravity is so strong that nothing can escape, produce vibrations that can be heard, not directly, but through their effects on surrounding matter. When two black holes orbit each other and eventually merge, they create ripples in space-time itself called gravitational waves. These waves were predicted by Einstein over a century ago, but they were not detected until 2016, when the Laser Interferometer Gravitational Wave Observatory, LIGO, picked up the signal from two colliding black holes over 1 billion light years away. The signal lasted only a fraction of a second, but when converted into sound, it produced a chirp, a rising tone that ended with a sudden drop. It was the sound of space-time ringing like a bell, the universe vibrating from the collision of two immense masses. Gravitational waves are a new way of observing the cosmos. Unlike light, which can be blocked by dust or absorbed by gas, gravitational waves pass through everything unimpeded. They carry information about events that would otherwise be invisible. The universe is now speaking to us not just in light, but in space-time itself, and we are learning to listen. There is something deeply peaceful about the silence of space. It is not the oppressive quiet of an empty room, but the vast, open silence of a place where sound has never existed. It is a reminder that not everything needs to make noise to be important. Stars shine in silence. Planets orbit in silence. Galaxies rotate, collide, and merge without a whisper. The universe operates according to forces that do not shout. Gravity does not roar. Electromagnetism does not scream. They simply act quietly and reliably, shaping the cosmos according to laws that have held for billions of years. Astronauts who have spent time in space often describe the silence as one of the most striking aspects of the experience. Inside the spacecraft, there are fans, pumps, and equipment humming constantly, but outside, nothing. When they perform spacewalks, even their own breathing and heartbeat become the loudest sounds. The Earth rotates below them in complete silence. The sun blazes without sound. The stars, scattered across the black, do not hum or whisper. They simply shine. This silence is not empty. It is full of potential. It is the background against which everything else occurs. And in that silence, there is a kind of permission to be still. If the universe itself can be quiet, then so can we. There is no need to fill every moment with noise, with activity, with distraction. Silence is not the absence of something. It is a presence in its own right, a space where thoughts can settle, where awareness can expand, where the mind can rest. Yet even in this silence, the universe is vibrating. Planets spin on their axes. Moons orbit planets. Stars orbit the centers of galaxies. Galaxies move through space, pulled by gravity toward unseen masses. Everything is in motion, and motion is rhythm. The universe has a beat, even if we cannot hear it. The Earth completes one rotation every 24 hours. It orbits the Sun every 365 and a quarter days. The Moon orbits Earth every 27 days. These are the rhythms that govern tides, seasons, and the passage of years. They are cosmic metronomes, keeping time without sound. Our solar system itself is moving. It orbits the center of the Milky Way galaxy at a speed of about 500,000 miles per hour, completing one orbit every 230 million years. This is called a galactic year. Dinosaurs roamed Earth during the last galactic year. The continents were in different positions. The climate was warmer, and yet, from our perspective, we do not feel this motion. We orbit the galaxy in silence, carried along by forces far larger than ourselves. Even individual atoms vibrate. Every molecule, every particle is in constant motion, jiggling and spinning at speeds determined by temperature. At absolute zero, the coldest possible temperature, motion would theoretically cease, but absolute zero has never been achieved and likely never will be. Even the vacuum of space, the emptiest regions far from stars and galaxies, still contains faint traces of energy, quantum fluctuations popping in and out of existence. The universe is never truly still. It hums with activity, though the hum is below the threshold of our senses. This silent symphony is not random. It follows rules. Physics, the language of cause and effect, dictates how objects move, how energy flows, how forces interact. These rules are the same everywhere. from the smallest subatomic particle to the largest galaxy cluster. Gravity always attracts. Light always travels at the same speed in a vacuum. Energy is always conserved. The universe is not chaotic. It is orderly, predictable, and profoundly peaceful in its consistency. And perhaps that is the most comforting fact of all. The silence of space is not empty or frightening. It is the canvas upon which the universe paints its story. It is the pause between notes that gives music its meaning. It is the stillness that allows motion to be seen. Without the silence of space, we could not hear ourselves think, could not see the stars, could not appreciate the gentle rhythms that keep everything in balance. The universe does not need to shout to be magnificent. It simply is, quietly and completely, and that is enough. Planets and moons, worlds of wonder. Our solar system is home to 8 planets, each with its own personality, its own weather, its own collection of moons and rings. These are not distant abstractions. They are worlds, some made of gas, some of rock, some of ice, each following ancient orbits around the sun with clockwork precision. And scattered among them are hundreds of moons, ranging from tiny captured asteroids to worlds larger than the planet Mercury, each with stories written in craters, canyons, and frozen seas. Let us begin with our own moon, the pale companion that lights our nights and governs our tides. The moon is Earth's only natural satellite, and it is unusually large compared to its parent planet. Most moons in the solar system are tiny compared to the worlds they orbit, but our moon is about 1/4 the diameter of Earth. This makes the Earth-Moon system almost a double planet, 2 worlds locked in a gravitational dance that has lasted for over 4 billion years. The moon is slowly drifting away from Earth. Every year, it moves about 1.5 inches farther from us. This happens because of tidal forces. The moon's gravity pulls on Earth's oceans, creating the bulges we call tides. As Earth rotates beneath these bulges, friction between the water and the ocean floor slows Earth's rotation ever so slightly. To conserve angular momentum, the moon must move farther away. Millions of years ago, the moon was much closer and Earth's days were shorter. In the distant future, the moon will be farther still and Earth's days will be longer. But this process is so gradual, so patient, that it reminds us once again how the universe operates on timescales that dwarf human experience. The moon always shows us the same face. This is called tidal locking, and it occurs because the moon's rotation period matches its orbital period exactly. It takes about 27 days for the moon to rotate once on its axis, and it takes the same amount of time to orbit Earth. This is not coincidence. Over billions of years, Earth's gravity has slowed the moon's rotation until it became synchronized with its orbit. The far side of the moon, often incorrectly called the dark side, is just as illuminated by the sun as the near side. But we never see it from Earth Spacecraft have photographed it, revealing a heavily cratered surface with fewer of the dark plains called Maria that mark the near side. Beyond our moon lie the planets. Mercury, the closest to the sun, is a scorched world where daytime temperatures reach 800 degrees Fahrenheit and nighttime temperatures plunge to negative 290 degrees. It has no atmosphere to trap heat or distribute it evenly, so the difference between day and night is extreme. Despite being named after the swift Roman messenger god, Mercury moves slowly on its axis, rotating once every 59 Earth days. This means a single day on Mercury lasts longer than a year on Mercury, which takes only 88 Earth days. Venus, often called Earth's twin because of its similar size, is anything but welcoming. Its thick atmosphere, composed mostly of carbon dioxide, traps heat in a runaway greenhouse effect, making Venus the hottest planet in the solar system despite being farther from the Sun than Mercury. Surface temperatures reach 900 degrees Fahrenheit, hot enough to melt lead. The atmospheric pressure is 90 times greater than Earth's, equivalent to being nearly a mile underwater. And the clouds are made of sulfuric acid. Yet, Venus has its own beauty. Its clouds reflect sunlight brilliantly, making it the brightest object in the night sky after the moon. Ancient cultures called it the morning star and the evening star, not realizing they were observing the same planet. Mars, the red planet, has long captured human imagination. It is smaller than Earth, with a thin atmosphere mostly composed of carbon dioxide. Its surface is cold, dry, and covered in rust-colored dust rich in iron oxide. But Mars was not always this way. Billions of years ago, it had a thicker atmosphere, liquid water flowing across its surface, and possibly conditions suitable for life. Today, water exists on Mars as ice at the poles and buried beneath the surface. Robotic rovers have explored its deserts, climbed its mountains, and studied its rocks, searching for signs that life may have once existed there. Mars has the largest volcano in the solar system, Olympus Mons, which stands nearly 14 miles high, almost 3 times the height of Mount Everest. It also has a canyon system, Valles Marineris, that stretches over 2,500 miles, long enough to span the width of the United States. Jupiter, the giant of the solar system, is more massive than all the other planets combined. It is a gas giant with no solid surface, just layers of hydrogen and helium growing denser toward the core. Jupiter's most famous feature is the Great Red Spot, a storm larger than Earth that has been raging for at least 350 years, possibly much longer. The storm rotates counterclockwise, driven by powerful winds that reach speeds of over 400 miles per hour. Despite its violence, the Great Red Spot is slowly shrinking, and scientists are not sure why. Jupiter has at least 95 known moons, including the 4 largest, Io, Europa, Ganymede, and Callisto, discovered by Galileo in 1610. Europa is particularly intriguing Beneath its icy crust lies a global ocean of liquid water, kept warm by tidal heating from Jupiter's gravity. This ocean may contain more water than all of Earth's oceans combined. And where there is liquid water, there is the possibility of life. Saturn, the ringed jewel of the solar system, is almost as large as Jupiter, but less dense. In fact, Saturn is so light for its size that it would float in water if you could find a bathtub large enough. Its rings are made of countless particles of ice and rock, ranging in size from grains of sand to house-sized boulders, all orbiting the planet in a thin disk that stretches hundreds of thousands of miles, but is only tens of meters thick in most places. The rings are not solid. They are billions of individual objects, each following its own orbit, held in place by Saturn's gravity and shaped by the gravitational influence of its many moons. Saturn has at least 146 known moons, including Titan, the only moon in the solar system with a thick atmosphere. Titan's atmosphere is denser than Earth's, and its surface is dotted with lakes and seas, not of water, but of liquid methane and ethane. It rains on Titan, slow drops of organic compounds falling from the hazy orange sky. Uranus and Neptune, the ice giants, orbit in the cold outer reaches of the solar system. Uranus is tilted on its side, likely the result of a massive collision early in its history, so its poles point nearly toward the Sun during parts of its 84-year orbit. This gives Uranus the most extreme seasons in the solar system, with each pole experiencing 42 years of continuous daylight, followed by 42 years of darkness. Neptune, the farthest planet, is a deep blue world with the fastest winds in the solar system, reaching speeds of over 1,200 miles per hour. Both planets have rings, though they are faint and difficult to see compared to Saturn's spectacular bands. Even beyond Neptune, the solar system continues. The Kuiper Belt, a region of icy bodies beyond the orbit of Neptune, contains thousands of small worlds, including Pluto, which was reclassified as a dwarf planet in 2006. Pluto has 5 known moons, the largest of which, Charon, is so big relative to Pluto that they orbit a common center of mass between them. The two worlds are locked in a mutual tidal embrace, always showing the same face to each other. Beyond the Kuiper Belt lies the Oort cloud, a vast sphere of icy objects surrounding the solar system, extending nearly halfway to the nearest star. Comets originate from the Oort cloud, dislodged by gravitational disturbances and sent tumbling toward the inner solar system, where the sun's heat vaporizes their ice, creating the glowing tails we see from Earth. All of these worlds, all of these moons, are part of our cosmic neighborhood. They are not unreachable fantasies. We have sent spacecraft to visit every planet in the solar system. We have landed rovers on Mars, dropped probes into Jupiter's atmosphere, and orbited Saturn for over a decade. The Voyager spacecraft, launched in the 1970s, have traveled beyond the edge of the solar system and are now in interstellar space, carrying golden records with sounds and images from Earth. messages in a bottle cast into the cosmic ocean. And beyond our solar system, there are other planets. Thousands of them. Astronomers have discovered over 5,000 exoplanets orbiting other stars, and the count grows almost daily. Some are gas giants, larger than Jupiter. Others are rocky, worlds similar to Earth. Some orbit so close to their stars that their surfaces are molten. Others are so far out that they are frozen solid. A few orbit in the habitable zone, the region where temperatures are just right for liquid water to exist on the surface. These are the worlds where life, as we know it, might be possible. One day, perhaps centuries from now, humans may walk on some of these distant worlds. But even if we never leave our own planet, knowing they are there, knowing that the universe is filled with worlds beyond counting, is enough to inspire wonder. We are not alone in the cosmic sense. We are part of a vast family of planets, moons, and stars, all moving through space together, all governed by the same laws of physics, all made of the same elements forged in the hearts of dying stars. The universe is not empty. It is teeming with worlds, each with its own beauty, its own mysteries, its own silent story unfolding across billions of years. And every one of them, from the smallest asteroid to the largest gas giant, is part of the same cosmic dance that includes us. The infinite scale of everything. One of the most humbling and strangely comforting facts about the universe is its sheer scale. The numbers involved are so large that they become almost meaningless. Yet when we truly try to grasp them, they offer a kind of peace. Our problems, our worries, the things that consume our daily thoughts, all of it shrinks to near invisibility against the backdrop of cosmic immensity. This is not to say our lives do not matter. They do. But the universe reminds us that we are part of something unimaginably larger, older, and more enduring than any single moment of anxiety or fear. Let us start small. You are made of cells, about 37 trillion of them, each one a microscopic world unto itself. Inside each cell are organelles, tiny structures that perform specific functions. And inside the nucleus of each cell is your DNA, a molecule containing about 3 billion base pairs of genetic information. If you could unwind all the DNA in a single cell and stretch it out, it would be about 6 feet long. If you did this with every cell in your body, the DNA would stretch for over 10 billion miles, enough to reach from Earth to Pluto and back several times. You contain multitudes. Now, let us zoom out. Earth is about 8,000 miles in diameter, large enough that you could fit about 130 Earths side by side across the diameter of the Sun. The Sun itself is vast, but it is only one star among hundreds of billions in the Milky Way galaxy. If you wanted to count all the stars in our galaxy, counting one per second without stopping, it would take you over 9,000 years. And the Milky Way is just one galaxy among trillions in the observable universe. The observable universe, the part of the universe we can see from Earth, is about 93 billion light years in diameter. A light year is the distance light travels in 1 year, roughly 6 trillion miles. This means the observable universe is about 550 sextillion miles across. To put that in perspective, if you could travel at the speed of light, the fastest speed possible, it would take you 93 billion years to cross from one side to the other, far longer than the current age of the universe, which is about 13.8 billion years. The reason the observable universe is larger than its age would suggest is because space itself is expanding, carrying distant galaxies away from us faster than light can travel. There are more stars in the universe than grains of sand on all the beaches and deserts of Earth. This comparison, made famous by Carl Sagan, was later confirmed by scientists who calculated both numbers. The universe contains approximately 300 sextillion stars, while Earth contains roughly 7 quintillion, 500 quadrillion grains of sand. The stars win. For every grain of sand on our entire planet, there are dozens of stars shining in the cosmos. Each of those stars is a sun, many with planets, moons, and asteroid belts of their own. The universe is not sparse. It is abundant beyond comprehension. Yet despite this abundance, the universe is mostly empty space. If you removed all the atoms from the universe and left only the empty space between them, the difference would be almost imperceptible, because atoms themselves are mostly empty space. The nucleus of an atom, containing protons and neutrons, is incredibly tiny compared to the cloud of electrons that surrounds it. If an atom was scaled up to the size of a football stadium, the nucleus would be about the size of a pea sitting at the center of the field, and the electrons would be zipping around somewhere in the stands. Everything in between is emptiness. This emptiness extends to the cosmos. The distance between stars is vast. The nearest star to our Sun, Proxima Centauri, is over 4 light years away. If you imagine the Sun as a grain of sand, Proxima Centauri would be another grain of sand about 4 miles away. The space between them is empty, dark, and silent. Galaxies are even more spread out. The nearest large galaxy to the Milky Way, Andromeda, is about 2.5 million light years away. Yet even with such distances, galaxies are not randomly scattered. They cluster together in groups, which cluster into superclusters, which form filaments and sheets separated by vast voids where few galaxies exist. The universe has structure, like a cosmic web stretching across space. If you could somehow stand outside the universe and look at it all at once, you would see this web, threads of galaxies glowing like strings of lights against an infinite darkness. The voids between them are not truly empty. They contain dark matter and dark energy, mysterious substances that make up most of the universe's mass and energy, but do not emit light or interact with ordinary matter in any way we can directly observe. Dark matter provides the gravitational glue that holds galaxies and galaxy clusters together. Dark energy drives the accelerating expansion of the universe, pushing galaxies apart faster and faster as time goes on. The scale of time is equally staggering. The universe is 13.8 billion years old. Give or take a few 100 million years. Earth formed about 4.5 billion years ago, roughly 1/3 the age of the universe. Life on Earth appeared relatively quickly after that, within the first billion years. Simple, single-celled organisms dominated for billions of years before complex life emerged. Dinosaurs appeared about 230 million years ago and went extinct 66 million years ago. Modern humans, Homo sapiens, have existed for only about 300,000 years, a blink in cosmic time. Recorded history covers only the last 5,000 years or so. The entire span of human civilization, from the first cities to the present day, represents less than 1/10,000th of 1% of the universe's age. Put another way, if the history of the universe were compressed into a single year, with the Big Bang occurring at midnight on January 1st, Earth would not form until September. Life would appear in late September. Dinosaurs would roam the Earth for a few hours in late December. They would go extinct on December 30th. Modern humans would appear in the last few minutes before midnight on December 31st. All of recorded history would occur in the final second of the year. This perspective is both humbling and liberating. Your life, with all its joys and struggles, is a brief spark in the vast darkness of time. But it is your spark. You are part of this story, woven into the fabric of a universe that began almost 14 billion years ago and will continue for trillions of years to come. The atoms in your body are ancient, formed in stars that died long before Earth existed. The water you drink was once part of comets that bombarded the young Earth billions of years ago. The oxygen you breathe was produced by plants through photosynthesis, a process powered by sunlight, which is powered by nuclear fusion, which is powered by gravity. Everything is connected across space and time. And yet, despite the universe's immensity, we are not insignificant. We are the part of the universe that has become conscious, that can observe and understand itself. We are made of star stuff, as Carl Sagan famously said. Matter that has organized itself into structures capable of thought, emotion, creativity, and wonder. The universe, through us, is aware of its own existence. That is not insignificance. That is extraordinary. When you feel small, remember that you are part of something infinitely large. When you feel overwhelmed, remember that the universe itself is patient, unfolding according to laws that have held steady for billions of years. When you feel alone, remember that you are made of the same material as stars, connected to everything that has ever existed or ever will exist. The scale of the universe is not meant to diminish you. It is meant to remind you that you belong to it, and it belongs to you. Black holes, gentle giants of gravity. Black holes have a fearsome reputation. They are often portrayed as cosmic monsters, devouring everything that comes near, tearing apart stars and swallowing planets whole. And in some sense, this is true. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon, the boundary beyond which escape is impossible. But black holes are not predators. They do not hunt, they do not reach out and grab things from a distance. They simply sit in space, following the same laws of gravity as any other massive object, only more so. A black hole is what remains when a massive star, at least 20 times the mass of the Sun, exhausts its nuclear fuel and collapses under its own gravity. The collapse is sudden and catastrophic. The outer layers of the star are blown away in a supernova explosion, while the core continues to collapse, compressing matter to infinite density in a point called a singularity. The singularity is surrounded by the event horizon, a spherical boundary whose size depends on the mass of the black hole. For a black hole with the mass of the Sun, the event horizon would be only about 2 miles across. For a supermassive black hole with a mass of billions of suns, the event horizon could be larger than our solar system. Despite their power, black holes are not vacuum cleaners. They do not suck up everything around them. If the Sun were suddenly replaced by a black hole of equal mass, Earth would continue to orbit exactly as it does now. The gravitational pull at Earth's distance would be unchanged. The difference is that you could no longer see the black hole, and if you traveled close enough to the event horizon, the effects of gravity would become extreme. But from a safe distance, a black hole is no more dangerous than any other massive object. In fact, black holes can be remarkably stable and long-lived. Once formed, they can exist for trillions of years, slowly evaporating through a process called Hawking radiation, named after physicist Stephen Hawking. Hawking radiation is a quantum effect that occurs near the event horizon, where pairs of particles and antiparticles spontaneously form, and occasionally one escapes while the other falls in, causing the black hole to lose mass over time. For stellar mass black holes, this process is so slow that it would take longer than the current age of the universe for a black hole to evaporate completely. Supermassive black holes would take even longer, on the order of 10 to the 100th power years, a time so long it is almost meaningless. Black holes warp space-time in ways that defy everyday intuition. Near a black hole, time slows down dramatically compared to regions far from the gravitational influence. If you could watch someone fall toward a black hole from a safe distance, you would see them slow down as they approached the event horizon, their movements becoming more and more sluggish until they appeared to freeze in place, never quite crossing the boundary. This is time dilation taken to its extreme. From the perspective of the person falling, however, time would pass normally. They would cross the event horizon in a finite amount of time, unaware that the rest of the universe was speeding up around them. This time dilation effect has been depicted in science fiction films, most famously in Interstellar, where astronauts visit a planet orbiting close to a massive black hole and experience time passing much slower than for their colleagues waiting in orbit. 1 hour on the planet equals 7 years for the people far from the black hole. This is not fantasy. It is an accurate representation of how gravity affects time, though the specific numbers depend on the mass of the black hole and the distance from it. At the center of most galaxies, including our own Milky Way, lies a supermassive black hole. The one at the heart of the Milky Way is called Sagittarius A star, and it has a mass of about 4 million suns. Despite its enormous mass, it is relatively quiet. It does not emit much light or radiation because it is not currently consuming large amounts of material. Occasionally, a star or cloud of gas ventures too close and is torn apart by tidal forces, a process called spaghettification, where the difference in gravitational pull between the near and far side of an object stretches it into a long, thin strand. But most of the time, Sagittarius A star simply sits at the galactic center, holding the galaxy together through its gravitational influence. Astronomers have taken the first direct image of a black hole's event horizon, or rather, the glowing ring of superheated materials surrounding it. In 2019, the Event Horizon Telescope, a global network of radio telescopes working together, captured an image of the supermassive black hole at the center of the galaxy, Messier 87, about 55 million light-years from Earth. The image shows a bright ring of light surrounding a dark shadow, the shadow cast by the event horizon itself. The light comes from an accretion disk, a swirling disk of gas and dust spiraling into the black hole, heated to billions of degrees by friction and gravitational compression. The image is a triumph of science and technology, proof that black holes are not just theoretical constructs, but real objects that can be observed and studied. Black holes also play a crucial role in the evolution of galaxies. The energy released by material falling into a supermassive black hole can be enormous, sometimes outshining the entire galaxy. This energy can heat and disperse gas in the galaxy, regulating star formation and shaping the structure of the galaxy over billions of years. Black holes are not just destroyers. They are sculptors, shaping the galaxies they inhabit. In the far future, long after the last stars have burned out, black holes will be among the last remaining objects in the universe. They will drift through the darkness, slowly evaporating, until eventually even they fade away, leaving behind only the faint whisper of Hawking radiation and the cold, empty expanse of space. But that future is so distant, trillions upon trillions of years from now, that it is beyond comprehension. For now, black holes are landmarks in the cosmic landscape, places where the laws of physics are pushed to their limits, where time and space behave in ways that challenge our understanding. And yet, for all their strangeness, black holes follow the same rules as everything else in the universe. They are governed by gravity, by the curvature of space-time, by the equations that describe how mass and energy interact. They are not supernatural. They are natural consequences of the universe's laws, reminders that even the most extreme phenomena arise from principles we can understand, measure, and predict. Black holes are not to be feared. They are to be studied, appreciated, and admired as some of the most fascinating objects in the cosmos. The ancient light that surrounds us. When you look at the sky, whether at stars, galaxies, or the faint glow of the Milky Way, you are looking backward in time. Light takes time to travel, and the farther away an object is, the longer its light has been traveling to reach you. This means that the universe is not just a place. It is also a timeline, a living archive of its own history written in light. The light from the sun takes about 8 minutes and 20 seconds to reach Earth. This means that when you look at the sun, you are seeing it as it was 8 minutes ago, not as it is right now. If the sun suddenly vanished, we would not know for 8 minutes. The light and heat it emitted moments before disappearing would still be traveling toward us, and Earth would continue to orbit an invisible point in space until the last photons arrived and the sky went dark. The nearest star, Proxima Centauri, is over 4 light-years away. When you see it in the night sky, you are seeing light that left the star over 4 years ago. If Proxima Centauri had exploded last year, we would not know for another 3 years. The farther you look, the farther back in time you see. A star 100 light-years away appears as it was when your great-grandparents were young. A galaxy 1 million light-years away appears as it was when early humans were learning to walk upright. A galaxy 1 billion light-years away appears as it was long before Earth existed. The farthest objects we can see are galaxies so distant that their light has been traveling for over 13 billion years, almost as long as the universe itself has existed. These galaxies appear not as they are now, but as they were when the universe was young, less than 1 billion years old. They are small, dim, and irregular, unlike the large spiral and elliptical galaxies that dominate the universe today. By studying them, astronomers can piece together the history of the cosmos, watching how galaxies formed, grew, and evolved over billions of years. But there is something even more ancient than the light from distant galaxies. It is called the cosmic microwave background, and it is the oldest light in the universe. The cosmic microwave background, CMB, is the faint glow of radiation left over from the Big Bang. About 380,000 years after the universe began, it had cooled enough for the first atoms to form. Before this moment, the universe was a hot, dense plasma of particles and light, opaque and glowing like the surface of a star. But when atoms formed, the universe became transparent for the first time. Light that had been trapped in the plasma was suddenly free to travel through space. That light, stretched and cooled by the expansion of the universe, is the cosmic microwave background. Today, the CMB appears as a faint microwave radiation coming from all directions in the sky. With a temperature of about -270 degrees Celsius, just a few degrees above absolute zero. It is remarkably uniform, varying by only 1 part in 100,000 from place to place. These tiny variations are significant though. They represent slight differences in density in the early universe, seeds that would eventually grow into galaxies and galaxy clusters under the influence of gravity. Satellites like the Cosmic Background Explorer, launched in 1989, and the Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the cosmic microwave background with increasing precision, revealing its structure in exquisite detail. The patterns in the CMB tell us about the composition of the universe, its age, its geometry, and its eventual fate. They confirm that the universe is about 13.8 billion years old, that it is flat rather than curved, and that it is composed mostly of dark matter and dark energy, with ordinary matter making up only about 5% of the total. The cosmic microwave background is everywhere. It passes through you right now, a constant stream of ancient photons that have been traveling for over 13 billion years. These photons were created when the universe was a hot, glowing fog, and they have been journeying ever since, cooling and stretching as space expanded around them. When you tune an old analog television to a channel with no signal, about 1% of the static you see is caused by the cosmic microwave background. You are watching the afterglow of the Big Bang. This ancient light is a gift. It is the universe's baby. Picture a snapshot of what everything looked like when it was young. By studying it, scientists can test theories about the origin and evolution of the cosmos. They can measure the rate of expansion, the density of matter, the nature of dark energy. They can even look for signs of what came before the Big Bang. Though this remains speculative, there is a profound peace in knowing that the universe has left us this message. It has preserved a record of its own beginning, encoded in light, waiting for us to discover and decode. We are not stumbling blindly through existence. We are uncovering the story of where we came from, written in the oldest light imaginable. And the story it tells is one of gradual change, of structure emerging from near uniform simplicity, of matter gathering under gravity's patient pull, of stars igniting, galaxies forming, planets coalescing, and eventually life arising to contemplate it all. The cosmic microwave background is the starting point, the canvas on which everything else was painted. It is the silent witness to the birth of everything. When you look at the CMB, you are looking at a time when the universe was small, dense, and featureless, just beginning to hint at the complexity it would become. You are seeing potential, the raw ingredients from which everything was made. And in a way, you are seeing yourself, because every atom in your body, every particle of matter around you was once part of that hot, glowing plasma. You are made of the same stuff that filled universe in its infancy. You are a continuation of that ancient light, transformed and reshaped over billions of years, but still connected to the very beginning. Cosmic companions, we are never alone. The universe is vast, but it is not empty. And even though the distances between stars and galaxies are immense, we are not isolated. We are part of a cosmic community, connected to our neighbors by gravity, by shared origins, and by the simple fact that we all exist within the same expanding space. Our closest cosmic companion is the Andromeda Galaxy, also known as Messier 31. It is a large spiral galaxy similar to the Milky Way, containing about 1 trillion stars compared to our galaxy's 200 to 400 billion. Andromeda is about 2.5 million light-years away, making it the most distant object visible to the naked eye on a clear dark night. It appears as a faint smudge in the constellation Andromeda, but through a telescope, it reveals itself as a magnificent spiral with bright arms and a glowing core. Andromeda is not just sitting quietly in space. It is moving, and it is moving toward us. Andromeda and the Milky Way are on a collision course, pulled together by their mutual gravitational attraction. In about 4.5 billion years, the two galaxies will begin to merge. This sounds catastrophic, but it will not be. Galaxies are mostly empty space, and the stars within them are so far apart that collisions between individual stars will be extremely rare. Instead, the galaxies will pass through each other, their shapes warping and distorting, their spiral arms flung outward by gravitational forces. Over hundreds of millions of years, they will merge into a single, larger galaxy, likely an elliptical galaxy rather than a spiral. Astronomers have nicknamed this future galaxy Milkomeda. This merger is not something to fear. By the time it happens, Earth will likely be uninhabitable for other reasons. The Sun will be nearing the end of its main sequence life, growing hotter and brighter, eventually expanding into a red giant that will engulf the inner planets. But even if Earth survives, the view from the night sky will be spectacular. As the galaxies approach, Andromeda will grow larger and larger, eventually stretching across the sky like a glowing river. During the merger, new stars will form in great numbers as gas clouds collide and compress, triggering waves of star formation that will light up the combined galaxy. It will be one of the most beautiful events in cosmic history, and it will unfold over such long time scales that no single generation will notice the change. Beyond Andromeda, there are dozens of smaller galaxies in our local group, a collection of over 80 galaxies bound together by gravity. These include the Large and Small Magellanic Clouds, two irregular dwarf galaxies visible from the southern hemisphere, as well as numerous tiny dwarf galaxies scattered around the Milky Way and Andromeda. Some of these dwarf galaxies are in the process of being torn apart by the gravitational pull of their larger neighbors, their stars stripped away and absorbed into the Milky Way. This is how large galaxies grow, by cannibalizing smaller ones over billions of years. Our local group is part of an even larger structure called the Virgo supercluster, a massive collection of galaxy groups and clusters spanning over 100 million light-years. At the heart of the Virgo supercluster is the Virgo cluster, a dense concentration of over 1,000 galaxies. The gravity of the Virgo cluster is so strong that it is pulling our entire local group toward it, though the journey will take billions of years. Recent observations have revealed that the Virgo supercluster itself is part of an even larger structure called Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster of superclusters containing about 100,000 galaxies spread across 520 million light years. All the galaxies within Laniakea are moving toward a common gravitational center called the Great Attractor, a region of space with enormous mass that we cannot see directly because it lies behind the plane of the Milky Way, hidden by dust and gas. These structures, from local groups to superclusters, remind us that the universe is not random. It is organized, connected, and governed by forces that bind matter together across unimaginable distances. We are not drifting alone through an empty void. We are part of a cosmic web, a network of galaxies connected by gravity and the expansion of space. Even on smaller scales, we are not alone. Our solar system exists within the Orion Arm, one of the spiral arms of the Milky Way. We are about 26,000 light years from the galactic center, in a relatively quiet neighborhood with no nearby supernovae or massive star-forming regions. This is a good thing. Too close to the galactic center, and radiation levels would be dangerously high. Too far out, and there would be fewer heavy elements necessary for planet formation and life. We exist in what astronomers call the galactic habitable zone, a region where conditions are just right for planets like Earth to form and for life to emerge. Within our own solar system, we have neighbors that scientists are actively studying for signs of past or present life. Mars, with its ancient riverbeds and subsurface ice, may have once hosted microbial life. Europa, one of Jupiter's moons, has a global ocean beneath its icy crust that could harbor life in the dark, pressurized waters. Enceladus, a small moon of Saturn, has geysers that spray water vapor and organic molecules into space, suggesting hydrothermal vents on its ocean floor, similar to those on Earth where life thrives without sunlight. Titan, Saturn's largest moon, has lakes of liquid methane and a thick atmosphere rich in organic compounds, creating conditions that might support exotic forms of life completely different from anything on Earth. The search for life beyond Earth is one of the most profound scientific endeavors of our time. Astronomers are discovering exoplanets at an astonishing rate, and many of these planets orbit in the habitable zones of their stars, where temperatures allow liquid water to exist on the surface. Some of these planets are rocky, similar in size to Earth, and orbit small, cool red dwarf stars that are the most common type in the galaxy. If even a tiny fraction of these planets harbor life, the universe could be teeming with living worlds, each developing its own ecosystems, its own evolutionary paths, its own ways of adapting to the conditions around it. We have not yet found definitive proof of life beyond Earth. But the search continues. Missions are being planned to return samples from Mars, to drill through the ice of Europa, to study the atmospheres of exoplanets for biosignatures like oxygen and methane. We are listening for radio signals from intelligent civilizations through projects like SETI, the search for extraterrestrial intelligence. So far, the universe has been silent, or perhaps we have not yet learned how to hear. But the fact that we are looking, that we are reaching out into the cosmos with curiosity and hope, is itself a beautiful thing. And even if we are the only intelligent life in the universe, we are not truly alone. We are surrounded by the products of stellar evolution, by the light of distant suns, by the gravitational influence of unseen galaxies. We are connected to the cosmic microwave background, to the expansion of space, to the flow of time. We are part of a universe that is constantly moving, changing, evolving, and we are witnesses to its grandeur. In a sense, we are the universe's way of knowing itself. Through us, through our curiosity and our science, the cosmos becomes aware of its own existence. We are made of atoms, forged in stars, arranged in patterns that allow for consciousness, thought, and wonder. We are not separate from the universe. We are expressions of it, temporary but meaningful, brief but beautiful. So when you look up at the night sky and see the stars, the moon, the planets, remember that you are looking at family. You are seeing the same elements that make up your body, scattered across space and time. You are connected to everything you see, bound by the same forces, governed by the same laws, part of the same unfolding story. The universe is not a cold, hostile place. It is home, and we are never truly alone. The rhythm of cosmic cycles. The universe operates in cycles, patterns that repeat across time scales, both short and long. These cycles provide structure to the cosmos, creating rhythms that are as reliable as they are ancient. And in these rhythms, there is comfort. The universe is not chaotic or unpredictable. It follows patterns, and those patterns create a sense of order and continuity. The most familiar cycle is the rotation of Earth on its axis, creating the alternation of day and night. This cycle takes about 24 hours, and it has been remarkably stable for billions of years. Earth rotates from west to east, which is why the sun appears to rise in the east and set in the west. This rotation is gradually slowing down due to tidal forces from the moon, but the change is so small that a day lengthens by only about 1.7 milliseconds per century. At this rate, it will take millions of years before the change becomes noticeable. Earth also orbits the sun, completing one revolution every 365 and a quarter days. This cycle creates the seasons, as Earth's tilted axis causes different parts of the planet to receive varying amounts of sunlight throughout the year. When the northern hemisphere is tilted toward the sun, it experiences summer, while the southern hemisphere experiences winter. 6 months later, the tilt causes the opposite effect. This cycle of seasons has shaped life on Earth, driving migrations, dormancy, and reproduction patterns in countless species. The moon's orbit around Earth creates another cycle, one that governs the tides. The moon's gravity pulls on Earth's oceans, creating bulges of water on the side facing the moon and the side facing away. As Earth rotates beneath these bulges, coastal regions experience high and low tides roughly twice a day. This tidal cycle has been a constant feature of Earth's oceans for billions of years, shaping coastal ecosystems and influencing the behavior of marine life. The moon also goes through phases, cycling from new moon to full moon and back again every 29.5 days. These phases occur because we see different portions of the moon's sunlit side as it orbits Earth. When the moon is between Earth and the sun, we see the dark side, creating a new moon. When Earth is between the moon and the sun, we see the fully illuminated side, creating a full moon. The cycle of lunar phases has been used by humans for thousands of years to track time, plan agricultural activities, and mark religious observances. Beyond Earth, other cycles operate on much longer timescales. Our solar system orbits the center of the Milky Way galaxy, completing one orbit every 220 to 250 million years. This is called a galactic year or a cosmic year. During one galactic year, the solar system travels about 528,000 light-years through space. The last time the solar system was in its current position, dinosaurs had just begun to appear on Earth. The next time it completes an orbit, Earth will be unrecognizably different, shaped by forces we cannot predict. Stars themselves go through life cycles, though these cycles span millions or billions of years. A star forms from a collapsing cloud of gas and dust, ignites nuclear fusion in its core, spends the majority of its life steadily converting hydrogen into helium, then eventually exhausts its fuel and dies, either gently shedding its outer layers or exploding in a supernova. The remnants of the dead star, whether a white dwarf, neutron star, or black hole, continue to exist for billions or even trillions of years, slowly cooling and fading into darkness. But the material expelled into space is recycled, forming new clouds of gas and dust that will eventually collapse to form new stars. The cycle continues, generation after generation, across cosmic time. Galaxies also have cycles, though these are less regular and more chaotic. Galaxies form through the gradual accumulation of gas and dark matter, shaped by gravity into spirals, ellipticals, or irregular structures. Over billions of years, galaxies collide and merge, triggering bursts of star formation and reshaping their structures. The Milky Way has absorbed numerous smaller galaxies over its lifetime, and it will eventually merge with Andromeda. These mergers are part of the ongoing evolution of galaxies, a process that has been occurring since the first galaxies formed over 13 billion years ago. Even the universe as a whole goes through cycles, though on timescales so vast they are almost beyond comprehension. The universe began with the Big Bang, a moment when space, time, matter, and energy all came into existence. It has been expanding ever since, and that expansion is accelerating due to dark energy. In the far future, trillions of years from now, the universe will be cold, dark, and nearly empty, with the last stars having burned out and black holes slowly evaporating through Hawking radiation. This is sometimes called the heat death of the universe, a state of maximum entropy where no energy gradients exist and no processes can occur. But some theories suggest that even this may not be the end. There are speculative ideas about cyclic universes, where the expansion eventually reverses into a contraction, culminating in a big crunch that is followed by another Big Bang, creating a new universe with new laws of physics. Other theories propose that our universe is just one of many in a multiverse, where new universes are constantly being created through quantum fluctuations or black hole formations. These ideas remain unproven and may be unprovable, but they remind us that even the largest cycles, the birth and death of universes, may be part of an even greater pattern. For now, we exist within these cycles, moving with them, shaped by them, part of the endless rhythm of the cosmos. Day follows night, the seasons turn, the moon waxes and wanes, Earth orbits the sun orbits the galaxy. Galaxies evolve and merge, the universe expands, and through it all, there is a sense of continuity, a reassurance that the universe follows rules, that patterns repeat, that nothing is truly random or meaningless. These cycles are not prisons. They are frameworks, structures that give the universe its shape and character. They are the reason we can predict eclipses, plan missions to other planets, and understand the history of the cosmos. They are the reason we can look at the night sky and see the same constellations our ancestors saw thousands of years ago, even though the stars themselves are slowly drifting through space. The universe changes, but it does so gradually, patiently, according to laws that we can learn and understand. And in that understanding, there is peace. We are not lost in chaos. We are riding the rhythms of the cosmos, carried along by forces that have been at work for billions of years and will continue for billions more. We are part of something larger than ourselves, something that moves with purpose and grace, something that does not rush or falter. The universe knows its own pace, and we are privileged to witness it, to study it, and to find our place within its endless cycles. The wonder of cosmic chemistry. Every element in the periodic table, from hydrogen to uranium and beyond, has a cosmic origin. The universe began with only the lightest elements, hydrogen and helium, created in the first few minutes after the Big Bang. Everything else, all the heavier elements that make up planets, life, and technology, was forged inside stars, or created in the violent explosions that mark their deaths. We are made of stardust, and so is everything around us. The process begins with hydrogen, the simplest and most abundant element in the universe. A hydrogen atom consists of one proton and one electron. and it makes up about 75% of the universe's ordinary matter. When gravity pulls hydrogen together into dense clouds, the pressure and temperature at the core eventually become high enough to initiate nuclear fusion. Two hydrogen nuclei combine to form helium, releasing energy in the process. This is the reaction that powers stars, including our sun, and it is the reason stars shine. Fusion does not stop with helium. In more massive stars, once the hydrogen in the core is exhausted, the core contracts and heats up until it is hot enough to fuse helium into heavier elements like carbon and oxygen. This process continues through successive stages, with each new fuel requiring higher temperatures and pressures. Stars massive enough can fuse elements all the way up to iron, creating layers of different elements like an onion. The core consists of iron, surrounded by shells of silicon, magnesium, neon, oxygen, carbon, helium, and finally hydrogen in the outer layers. But fusion stops at iron. Iron is the most stable element, and fusing it requires more energy than it releases, so the process is no longer self-sustaining. When a massive star's core becomes iron, it can no longer support itself against gravity. The core collapses in a fraction of a second, and the outer layers rebound in a catastrophic explosion called a supernova. The explosion releases more energy in a few seconds than the star emitted during its entire lifetime, and it creates conditions extreme enough to forge elements heavier than iron, including gold, silver, platinum, and uranium. These heavy elements are scattered into space by the explosion, mixing with clouds of gas and dust, and eventually becoming part of new stars, planets, and, in some cases, living organisms. The iron in your blood, the calcium in your bones, the oxygen you breathe, the carbon that forms the basis of organic chemistry, all of it was created inside stars that lived and died long before the sun and earth existed. You are literally made of stardust, and so is everything you touch, see, and interact with. This cosmic recycling has been going on for over 13 billion years, enriching the universe with heavier elements in each generation of stars. The first stars, formed from the hydrogen and helium created in the Big Bang, contained no heavy elements at all. These stars, called population 3 stars, were massive and short-lived, burning through their fuel quickly and exploding in supernovae that seeded the universe with the first carbon, oxygen, and iron. Later generations of stars, including our sun, formed from gas clouds already enriched with these heavier elements, allowing for the formation of rocky planets and the emergence of life. The sun itself is a third-generation star, meaning it formed from material that had already been through at least 2 previous cycles of star formation and death. The heavy elements in the solar system, including those in Earth and in your body, are the legacy of countless stars that lived and died before the sun was born. In a very real sense, we are the children of the stars, inheritors of their chemical wealth. Water, essential for life as we know it, also has a cosmic origin. Water molecules consist of 2 hydrogen atoms and 1 oxygen atom. The hydrogen dates back to the Big Bang, while the oxygen was created inside stars. When these atoms combine, they form water, which can exist as ice, liquid, or vapor, depending on temperature. Water is abundant in the universe, found in comets, asteroids, the icy moons of the outer planets, and even in clouds of gas between stars. Some of the water on Earth may have been delivered by comets that bombarded the young planet billions of years ago, carrying water formed in the cold outer reaches of the solar system, or even in interstellar space. Organic molecules, the building blocks of life, are also found throughout the universe. Simple organic compounds like methane, ethane, and formaldehyde have been detected in clouds of gas and dust around young stars, on comets, and in the atmospheres of planets and moons. More complex molecules, including amino acids, have been found in meteorites that fell to Earth, proving that the chemistry of life can occur in space without the need for a planet or liquid water. This discovery has profound implications. If the building blocks of life are common in the universe, then life itself may be common as well. The exact conditions required for life to emerge are still not fully understood, but it seems likely that wherever liquid water, organic molecules, and a source of energy exist together, life has a chance to begin. This could mean that life exists on Mars, Europa, Enceladus, Titan, or on planets orbiting other stars. We do not know yet, but the chemical evidence suggests that we are not alone. The universe is a vast chemistry lab, conducting experiments on scales and timescales we can barely imagine. Stars are crucibles where elements are forged. Supernovae are furnaces where the heaviest elements are created. Planets are mixing bowls where chemicals combine and interact. And life, wherever it exists, is the ultimate expression of cosmic chemistry, matter organized into patterns that can grow, reproduce, adapt, and, in some cases, think. This perspective transforms how we see the world around us. A rock is not just a rock. It is a collection of atoms created inside a star billions of years ago, ejected into space, incorporated into the cloud that formed the solar system, and eventually condensed into a solid object. A tree is not just a tree. It is carbon, oxygen, nitrogen, and other elements drawn from the soil and air, arranged into living tissue through the process of photosynthesis, powered by sunlight from a star. You are not just you. You are a temporary arrangement of atoms that have existed for billions of years and will continue to exist long after you are gone, cycling through the universe in different forms. There is a strange comfort in this knowledge. You are not separate from the universe. You are part of it, made of the same stuff, governed by the same laws. The atoms in your body have been on an incredible journey, from the Big Bang to stellar cores, to supernova explosions, to the formation of the solar system, to the emergence of life on Earth, to you. And when you die, those atoms will continue their journey, perhaps becoming part of other living things, or rocks, or oceans, or returning to space to be incorporated into new stars and planets. Nothing is lost. Everything is recycled. The universe wastes nothing. This is the wonder of cosmic chemistry. It connects everything to everything else. It shows that the universe is not a collection of isolated objects, but a single, interconnected system where matter flows from one form to another, where energy transforms but never disappears, where the past, present, and future are linked by the atoms we are made of. It is a story written in elements, and we are part of that story. The patient unfolding of the cosmos. One of the most calming aspects of the universe is its patience. Nothing in the cosmos happens quickly by human standards. Stars take millions of years to form. Galaxies take billions of years to evolve. Even light from distant objects takes so long to reach us that we see the universe not as it is, but as it was. This vast patience is a reminder that there is no rush, no urgency, no need to force things to happen before their time. Consider the formation of a star. It begins with a cloud of gas and dust, a nebula drifting through space. The cloud may be hundreds of light years across, vast and diffuse, with a density barely greater than a vacuum. Gravity begins to pull the gas together, slowly, imperceptibly at first. Over thousands of years, denser regions within the cloud attract more material, growing larger and heavier. Over hundreds of thousands of years, these regions begin to collapse under their own weight, forming cores that heat up as they contract. Eventually, after millions of years, the core of one of these collapsing regions becomes hot and dense enough for nuclear fusion to ignite. A star is born, but even then, the process is gradual. The star settles onto the main sequence, where it will burn steadily for millions, billions, or even trillions of years, depending on its mass. There is no hurry. The star has all the time in the universe. The same patience applies to the evolution of galaxies. When the universe was young, small clumps of dark matter began to attract ordinary matter, forming the first proto-galaxies. These were small, irregular, and chaotic, filled with intense star formation as the gas within them collapsed and ignited. Over billions of years, these proto-galaxies merged and grew, gradually forming the large spiral and elliptical galaxies we see today. The process is still ongoing. Galaxies continue to collide and merge, and they will do so for billions of years to come. Even planetary systems form slowly. When a star ignites, it is surrounded by a disk of leftover gas and dust. Within this disk, particles collide and stick together, gradually building up larger and larger bodies. Dust grains become pebbles, pebbles become boulders, boulders become planetesimals, objects a few miles across. Planetesimals collide and merge to form protoplanets, and protoplanets eventually become planets. The entire process takes tens of millions of years, a blink in cosmic time, but an eternity by human standards. Earth itself formed about 4.5 billion years ago, and it has been changing ever since. The early Earth was a molten ball of rock, bombarded by asteroids and comets. Over time, it cooled, developed a solid crust, and acquired an atmosphere and oceans. Life emerged within the first billion years, but it remained simple, single-celled organisms for billions of years before complex life appeared. Multicellular life did not become common until about 600 million years ago, and humans have existed for only the last 300,000 years, a tiny fraction of Earth's history. This slow unfolding is not a flaw or a delay. It is the natural pace of the universe. Complex structures, whether stars, galaxies, or life, require time to develop. They cannot be rushed. They emerge from simpler structures through gradual processes driven by gravity, chemistry, and natural selection. There are no shortcuts in the cosmos. And yet, within this patient unfolding, there are moments of sudden change. Supernovae explode in seconds. Gamma-ray bursts release more energy in a few minutes than the sun will produce in its entire lifetime. Asteroids impact planets, causing mass extinctions and reshaping ecosystems. But even these sudden events are the culmination of long, slow processes. A supernova occurs when a star has spent millions of years fusing elements in its core. An asteroid impact occurs when an object has spent billions of years drifting through space until its orbit finally intersects with a planet. The sudden moments are punctuation marks in a much longer story. For us, living in a world that often feels rushed, where days slip by and years accumulate before we realize it, the universe's patience is a lesson. It reminds us that meaningful change takes time, that complex things cannot be built quickly, that growth and development require patience and care. The universe does not hurry, and neither should we. There is also a kind of peace in knowing that the universe will continue long after we are gone. The sun will shine for another 5 billion years. The Milky Way will continue to rotate for trillions of years. The expansion of the universe will continue indefinitely, or at least for longer than we can measure. Our lives are brief, but the universe is eternal, at least in practical terms. And knowing that the cosmos will endure, that the stars will keep shining, that the cycles will continue, is oddly comforting. We are not responsible for holding everything together. The universe does that on its own, with or without us. This does not mean our lives do not matter. They do. We are the universe's way of experiencing itself, of becoming conscious and aware. Every moment of joy, every discovery, every act of kindness, every thought and feeling is the universe experiencing something it could not experience otherwise. We are small, yes, but we are also unique. And in our brief time here, we have the privilege of witnessing the cosmos, of learning its secrets, of appreciating its beauty. The universe is patient, but it is also generous. It has given us a planet to live on, a sun to warm us, a moon to light our nights. It has given us eyes to see the stars, minds to understand the laws of physics, and hearts to feel wonder and awe. It has given us time, finite but sufficient, to live our lives, to love, to learn, to create, to explore. And when our time is done, the atoms that make up our bodies will return to the cosmos, to be recycled and reused, to become part of new stars, new planets, perhaps new life. Nothing is wasted. Everything continues. So as you lie here, breathing slowly, feeling the weight of your body against the surface beneath you, remember that you are part of this patient unfolding. You are part of a process that began nearly 14 billion years ago and will continue for trillions of years to come. You are not separate from it. You are woven into the fabric of space-time, connected to everything that has ever existed and everything that ever will exist. You are part of the universe, and the universe is patient. There is no rush. There is only the gentle, inexorable flow of time, carrying everything forward together toward an unknowable future. And in this moment, right now, you can rest, you can let go, you can trust that the universe will continue, that the stars will keep shining, that the cycles will keep turning. You do not have to hold anything together. You do not have to worry or plan or struggle. You can simply be here now, part of the cosmos, breathing in sync with the rhythm of existence, at peace in the vast, beautiful, patient universe. A gentle farewell to the stars, and so our quiet journey through the cosmos comes to rest. We have drifted through time and space, from the slow tick of cosmic clocks to the patient birth of stars, from the glowing clouds of nebulae to the silent expanse between galaxies. We have seen how light carries the past into the present, how atoms connect us to ancient stars, how cycles repeat across unimaginable scales, and how the universe unfolds with a patience that makes our worries seem small and our lives seem precious. The universe is not a place of chaos or indifference. It is a place of order, beauty, and gentle rhythms. It follows laws that have held steady for billions of years. It creates structure from simplicity. It recycles everything, wasting nothing, transforming matter and energy in an endless dance of creation and destruction. And through it all, it invites us to look up, to wonder, to learn, and to find our place within the grand story of existence. You are made of stars. You are connected to everything you see in the night sky. The iron in your blood was forged in a supernova. The calcium in your bones was created in the heart of a dying star. The oxygen you breathe was produced by ancient stars billions of years ago. You are not separate from the universe. You are part of it, woven into its fabric, temporary but meaningful, brief but beautiful. When you feel small, remember that you are made of the same stuff as galaxies. When you feel alone, remember that you are surrounded by the light of distant suns, by the gravitational embrace of planets and moons, by the ancient glow of the cosmic microwave background. When you feel rushed, remember that the universe moves with patience, that stars take millions of years to form, that nothing in the cosmos is in a hurry. And when you feel overwhelmed, remember that the universe is vast enough to hold all your worries, all your fears, all your hopes and dreams, and still have room for trillions of stars, billions of galaxies, and endless possibilities. You are part of something infinitely larger than yourself, and that is not meant to diminish you. It is meant to remind you that you belong, that you matter, that you are exactly where you are supposed to be. If you found peace in this journey through the cosmos, I invite you to like this video, to subscribe to Silent Scientist for more gentle explorations of the universe, or to share your thoughts in the comments below. It helps other dreamers, other wanderers, other seekers of peace find their way here, one quiet soul at a time. But for now, there is nothing left to do. The stars are shining, just as they always have, just as they always will. The universe is unfolding, patient and beautiful, carrying you along with it. You are safe, you are connected, you are part of the cosmos. Let your thoughts drift like clouds across a summer sky. Let your breath slow to the rhythm of the tide. Let your body sink into the softness of this moment, and let the infinite, eternal, gentle universe carry you toward rest. Good night.